This is a video walkthrough for practice 2F. Let's take a look at number 1. We're given the graph of f of x in blue, and we're asked to sketch the graph of each transformation. What we need to recognize is that the graph of y equals f of x plus 2 is a transformation of f of x's graph, and it moves it left 2. And that is because we have an x plus 2 on the inside of the function, which means we're going to change the input in the inverse direction. So that means subtracting 2 from all of the x's and moving the graph left 2. So I'm going to take every single point, move it left 2, and then connect to form the new graph. An alternate approach would be to use a table to take your inputs x and then add 2 to them, and then find the f of x plus 2 values. If you're going to use that table approach, what you need to recognize is that we have our input, that is what is on the inside of the function, and the output, which is the function value, in the second and third columns. The points of the original function should be entered in there, -4, 2, -2, 0, 0, 2, 1, 0, and 2, -2. In order to move from x plus 2 to x, we have to subtract 2. So -4 minus 2 is -6. -2 minus 2 is -4. 0 minus 2 is -2. 1 minus 2 is -1. And 2 minus 2 is 0. And what you'll notice is that the x and y pairs are the points on the graph given to the right. So you can use either approach. All right, let's take a look at number 2. For this graph, if we look at the equation, I see that there is a +3 on the outside of f of x, which means we're affecting the output variable or the vertical variable, and adding 3 to the y coordinates makes the graph move up 3. So we can simply move every single point up 3 units and connect to form the new graph. Or, if you prefer the table of values approach, in order of operations, we choose an x, take f of that x value, and then once the function value has been found, add 3 to it. And it's important to realize where our inputs and our outputs are. Inputs in the first column, outputs in the second column. That is where the points of the original function go, which are -4, 2, -2, 0, 0, 2, 1, 0, and 2, -2. To move from f of x to f of x plus 3, simply add 3 to each of those y values. And you'll notice that the x's and the y's, which are equal to f of x plus 3's, if we graph those ordered pairs, we're going to get that graph of the new function. Now let's take a look at number 3. For number 3, I see a times -1 on the outside of f of x. That means it's going to affect the vertical variable, and multiplying by -1 accomplishes a vertical flip or a vertical reflection. So if we just simply take the graph and reflect each point over the x-axis, that is, if it was below, it's above, and if it were above, it's below, that will give us the graph of the new function. If you prefer the table of values approach, we are taking our x values, finding their f of x values, and then multiplying the outside of that by -1. And again, we have our input and our output variables. That is where the points for the original function go, -4, 2, -2, 0, 0, 2, 1, 0, and 2, -2. And to get from f of x to the opposite of f of x, just take the opposite of each of those f of x values. And then we just graph the points x versus the y values in the last column. For number 4, we have a times -1, but on the inside of the function. That means it's affecting the input or horizontal variable. So this is a horizontal flip or a horizontal reflection. And that means that what was on the left side of the graph will now appear on the right. I'm going to reflect that left part over to the right, and what was on the right will now appear on the left. So we're just reflecting each point across the y-axis. If you prefer the table of values approach, we're picking our x values, taking their opposites, and then applying the function to those opposites of the x's. Our input and output values are the inside of the function and the resulting function value. That is where in our table we write the ordered pairs for the original function, -4, 2, -2, 0, 0, 2, 1, 0, and 2, -2. To get from the negative x values to the x values, we need to multiply by -1. That will give us 4, 2, 0, -1, and -2. If we graph the x's versus the y values, that will give us the graph of the new function. For number 5, I see a ×2 on the outside of the function. That means we're affecting the vertical variable, and that means the vertical variable is being multiplied by 2, which represents a vertical stretch. So we can simply multiply each y value by 2, and connect to form the new graph. Notice that any points that were on the x-axis remain on the x-axis. If you prefer the table of values approach, we're picking an x value, taking the function value of that, and then multiplying that times 2. And our input and our output values are the input and the output for the function. There is where our original ordered pairs go, -4, 2, -2, 0, 0, 2, 1, 0, and 2, -2. To find 2 times f of x, simply take the f of x values and multiply them by 2. And the first column and the last column give us our x's and our y's. Now let's look at number 6. In number 6, I see that the outside of the function is being multiplied by -1/2. That means that we're affecting the y variable, and there will be 2 things going on here that'll both be vertical since we're affecting the y variable. So there is a vertical compression with a factor of 1/2. That is to say, the y values are going to be half as big as the original ones. And then there is also a vertical flip because of the multiplication by -1. So each point is half as far as it was from the x-axis, but also on the opposite side. If you prefer the transformation approach, you can do that. If you prefer the table of values approach, x, f of x, and then last column, -1/2 times f of x. The input and output columns are the first 2. That's where the points for our original function go, -4, 2, -2, 0, 0, 2, 1, 0, and 2, -2. To find the -1/2 times f of x values, just take the f of x values and multiply by -1/2. And then graph those points given by the x's and the y's for the function, and that will produce that new graph. For number 7, you can observe that we have a -3 on the inside of the function, and so that means that we're affecting the x variable in the inverse direction. So we're going to add 3 to all the x's, which will move the graph right 3 units, and then a -2 on the outside of the function. That means that we're going to move the y variables. We're going to subtract the y variables, subtract 2 from the y variable, and that means that we're going to move the graph down 2. So you can just simply take every point and move right 3 and down 2. And connect the points to form the new graph. If you prefer the table of values approach, we'll have 4 columns: x, x minus 3, f of x minus 3, and then the last column will be f of x minus 3 minus 2. Our input and our output are the interior columns there, the second and the thirds. That's where the points for the graph of the original function go: -4, 2, -2, 0, 0, 2, 1, 0, and 2, -2. To move from x minus 3 to x, add 3. And then to move from f of x minus 3 to f of x minus 3 minus 2, subtract 2. And in the end, we can graph the x and y values, which are the first and last columns in the table. For number 8, I see a times -1 on the inside of the function. That's going to be a horizontal flip. And then I see a +2 on the outside of the function. That is a translation or shift up 2. So you can do these in either order, actually. And so if you want to do this in parts, you can take and do a horizontal flip. And there's the graph of the horizontal flip. And then move that graph up 2 for the final graph. And then if you're going to take that approach, be sure to erase the intermediate graph. All we want on there is the final answer. If you prefer the table of values approach, we're going to have 4 columns: x, the opposite of x, f of the opposite of x, and last column, f of the opposite of x plus 2. The input and the output columns are whatever's on the inside of the function and the function value of that expression. That's where our original function points go. So f of x's inputs and outputs go there. And to get from -x to x, take the opposite. And to get from f of -x to f of -x plus 2, add 2. And if we graph the ordered pairs given by the first column, comma, the last column, that will give us our x and y values. For number 9, I see a times -3 on the outside of the function. So those are going to be vertical changes. So we have a vertical stretch by a factor of 3. We also have a vertical flip, or a vertical reflection, since that number is negative that's being multiplied to the outside of the function. And then on the inside of the function, we have x plus 2. That's an input change, and that happens with inverse operations. That means we'll subtract 2 from all the x's, moving the graph left 2. That's a lot to keep track of. You may want to use your table of values approach for this one. So x followed by x plus 2 on the inside of the parentheses, and then f of x plus 2, and then the last column would be -3 times f of x plus 2. So our inputs and our outputs are the second and third columns. That's where the points for our original function go, -4, 2, -2, 0, 0, 2, 1, 0, and 2, -2. To move from x plus 2 to x, we subtract 2. And then to move from f of x plus 2 to -3 times f of x plus 2, multiply each by -3. And now we're going to graph our x's and our y's for the ordered pairs of the new function. So when x is -6, the y is -6. When x is -4, the y is 0. When x is -2, the y is -6. And then when x is -1, the y is 0. When x is 0, the y is 6. And so we wind up having a graph that looks like this. And I've done a lousy job with a straight line there. I'll do a better one here in a minute. There's our final graph. For number 2, we have two operations that are happening to the outside of the function. Since there are two separate that are happening to the outside, order actually is important. The first of these is a vertical stretch with the factor of 2, and the second is a shift up 1. When order matters, I would suggest using a table of values. X, f of x, then 2 times f of x, and finally last column would be 2 times f of x plus 1. Our input and our output columns are the first two, x and f of x. That's where the points for our original function go, -4, 2, -2, 0, 0, 2, 1, 0, and 2, -2. To find 2 times f of x, take the f of x values and multiply by 2. And then add 1 for the last column. And now we're going to graph the first column, x, versus the last column, which will be our y values. So -4, 5 is the first point, -2, 1, 0, 5. Just let me graph that last point correctly, -2, 1, 0, 5, 1, 0, and 2, -3. For number 11, we have two operations on the output variable as well. So it's important to follow order of operations here. The first is the multiplication. So that would be a vertical compression with a factor of 1/2. And then secondly, shift up 3. Since there are two transformations applying to the output variable, I would suggest using a table so that we get these in the correct order. X, f of x, and then 1/2 times f of x, and then the final column, 1/2 times f of x plus 3. Input and output are the first two columns, -4, 2, -2, 0, 0, 2, 1, 0, and 2, -2. To find 1/2 of f of x, take the f of x values and multiply by 1/2. And then add 3 to find the final values. And now we're going to graph the x's and the y's, which are in the final column, since y is equal to 1/2 times f of x plus 3. Negative 4 comma 4, negative 2 comma 3, 0 comma 4, 1 comma 3, and 2 comma 2. And we have a vertically compressed graph that's been moved up 3. And last, y equals negative f of x plus 5. Again, we have a multiplication and addition happening to the outside of the function, so both transformations are vertical. The multiplication one needs to happen first. That is a vertical flip, or a vertical reflection. And number 2, there's a shift up 5. Since there are two transformations both happening to the vertical variable, I would suggest using the table of values approach. X, f of x, the opposite of f of x, and the opposite of f of x plus 5 is our last column. Inputs and outputs are in the first two columns, negative 4 comma 2, negative 2 comma 0, 0 comma 2, 1 comma 0, and 2 comma negative 2. To find the opposite of the f of x's, take the f of x column and multiply each value by negative 1. And then add 5 to find the final column. Now we're going to graph the x's in the first column and the y's in the second column to give us our ordered pairs for the graph of the transformed function. Negative 4 comma 3, negative 2 comma 5, 0 comma 3, 1 comma 5, and 2 comma 7. And there's the graph of the transformed function. Moving to number 13, we have a piecewise defined function. G of x is equal to the absolute value of x minus 3 plus 1 for x's that are less than 1, and g of x equals x cubed plus x squared for x's that are greater than or equal to 1. So it's important to realize that g of 2 is asking us to replace x with 2. 2 is a value that is greater than 1, so we'll use the x cubed plus x squared function definition. 2 cubed is 8 and 2 squared is 4, so that means that g of 2 is equal to 12. In number 14, we are asked to find g of 0. Remember, 0 is the x value, and 0 is a value that is less than 1, so we're going to use the first part of the piecewise definition. G of 0 is the absolute value of 0 minus 3 plus 1, which would be the absolute value of negative 3 plus 1, and the absolute value of negative 3 is 3. 3 plus 1 is 4, so g of 0 is equal to 4. In number 15, we are asked to find the value of g of 1. 1 is included in the second interval because 1 is greater than or equal to 1. So we'll use the second part of the definition. G of 1 is equal to 1 cubed plus 1 squared. 1 cubed is 1, 1 squared is also 1, so g of 1 is equal to 2. For numbers 16 through 18, we're asked to find function values for h of x, which is a piecewise defined function with 3 pieces. H of 2 is asking us to consider a function value when x is equal to 2. X is equal to 2 falls on the interval between negative 1 and 2, inclusive of 2, so we'll use the second part of the function definition, 2x plus 1, to find the value of h of 2. So h of 2 is equal to 2 times 2 plus 1, which is 4 plus 1, or 5. In number 17, we're asked to find h of negative 5. Negative 5 is the x value, which means that negative 5 falls on the interval that's less than negative 1. So we'll use the first part of the definition for h of x, and that would be negative 5 squared plus 3. it's important to recognize that negative 5 belongs in parentheses there so that we are clear that we're squaring the negative value and not squaring just the 5. So negative 5 squared is 25. 25 plus 3 is 28. So h of negative 5 is 28. For number 18, we are asked to find h of 3. So 3 is the x value. 3 is greater than 2. So that means that h of 3 is equal to 4. And there's no computation to be done because h of x is equal to just the value 4 for that piece of the function. For 21 through 23, we're going to graph a piecewise function. My suggestion is to use a table of values for each piece of the function. So for the first part of the function, we're going to consider x values that are between negative 2 and 1. And I'm going to consider x values that are inclusive of those values, even though the interval doesn't include both negative 2, negative 1, 0, and 1. However, we'll notice that negative 2 is included in the interval, so when I find this value, I'm going to indicate this one with a closed circle, and then 1 is not included in the interval, so I'm going to indicate that ordered pair with an open circle when I graph. Now let's take a look at the values. So for x's between negative 2 and 1, the y value will be equal to 2x plus 1. And 2 times negative 2 plus 1 is negative 3. 2 times negative 1 plus 1 is negative 1. 2 times 0 plus 1 is 1. And 2 times 1 plus 1 is 3. Now let's graph those points on the grid to the right. Negative 2 comma negative 3, which is a closed circle for that endpoint. Negative 1 comma negative 1 is a point in the middle. 0 comma 1 is also a point in the middle, and 1 comma 3 is another endpoint, but that one needs an open circle, and I will have to graph that correctly this time. And there we have a straight line, or at least a part of a straight line. Now let's create a table of values for the other interval here. X is greater than or equal to 1. And we have x values, and our y's are equal to the opposite of the x's. For greater than or equal to 1, I'll start with 1 and start listing x values that are greater. I'll put a dot, dot, dot here. That means that we're going to finish off this part of the graph with an arrow that will be pointing to the right. Our y's are equal to the opposite of the x values. So these give us some points to graph. There's an arrow on the right, but 1 comma negative 1, since 1 is the x value that's included in this interval, will need a closed circle on that endpoint. So 1 comma negative 1 closed, 2 comma negative 2, 3 comma negative 3, 4 comma negative 4, and the graph continues in that direction with an arrow. For number 22, this is a 3-piece piecewise function. So our first table of values will be for x values that are less than negative 2. So I'm going to start with negative 2, even though that is not included. This point will get an open circle. And then values that are less than that, negative 3, negative 4, etc. And our y values here are equal to 3/2 times x plus 1. So 3/2 times negative 2 is negative 3 plus 1 is negative 2. If you prefer to skip over negative 3 since it's not an even number, you can. So we could skip to negative 4. Negative 4 times 3/2 is negative 6. Negative 6 plus 1 is negative 5. And then we can skip to the next even number since that's divisible by 2. Negative 6 times 3/2 is negative 9. Negative 9 plus 1 is negative 8. and then we're just going to continue from there. So I'm going to graph these points. -2, -2, open circle. -4, -5, closed circle. And I don't think we're going to be able to graph, well, we can't graph that last point, but the graph's just going to continue going down there, and we'll have an arrow on the end. Since x is less than 2, we'll continue to go in the leftward direction. For the next interval, x's will be between -2 and 0, inclusive at both endpoints. So my x values will be -2, -1, and 0. Both of those endpoints are included, so both endpoints will get a closed circle. And our y values are always equal to 3 for this piece of the graph. So the y values are 3. Now let's graph those ordered pairs. -2, 3, closed circle. -1, 3 in the middle of that interval, and 0, 3, the other end of the interval, gets a closed circle. There's a graph of that piece of the function. And the last piece for x greater than 0 are x values. And we'll use 0 to start with, even though it's not included. That point will get an open circle for that endpoint of that interval. And then 1, 2, 3 if we get that far. And our y values here are equal to x squared. 0 squared is 0, 1 squared is 1, 2 squared is 4, 3 squared is 9. 0, 0 gets an open circle. 1, 1, 2, 4, and we can't graph 3, 9, but this should be a familiar parent function to y equals x squared, but we're just looking at the right half of that parabola. And then an arrow on the end to indicate that x is greater than 0 continues rightward. We'll graph one more piecewise function. This has 3 pieces, so I'll make 3 tables. X is less than or equal to 0. So x, let's start with 0 and continue in a less than direction. And the graph will keep going. And our y values are equal to -1 times x squared plus 4. If x is 0, then 0 squared is 0 times -1 is still 0 plus 4 is 4. -1 squared is 1, but the opposite is -1 plus 4 is 3. -2 squared is 4, the opposite is -4 plus 4 is 0. And -3 squared is 9. The opposite of that is -9 plus 4 is -5. And that first point, the endpoint of the interval where x is equal to 0, is included in the interval, so we'll put a closed circle there. 0, 4, and then -1, 3, -2, 0, and -3, -5. And the graph continues leftward. The next interval is for x between 0 and 2, and our x's that can be used for that are 0, 1, and 2. Notice that neither endpoint is included in the interval, so that means that each of these points here will get an open circle. And for this interval, the y's are equal to 4, so that means no matter what, the y's are 4. So now we have 0, 4 with an open circle. Now if you look on the graph, when we go to graph that, 0, 4 has already been graphed, so we're not going to unclose that circle. There still is a point there. We will not include the open circle there. That just means the 2 pieces meet up in the same position. Now we have 1, 4 and 2, 4. So in between those, the graph is just a horizontal line, but I forgot at the right endpoint 2, 4 there is an open circle. And for the last part of the piecewise function, the x's are greater than or equal to 2. So our x's will be 2 or greater, 2, 3, 4, etc. And our y's will be equal to x minus 3. And since x is equal to 2 is included in the interval, that's going to get a closed circle. So to get the y's, subtract 3 from each x. 2 minus 3 is negative 1, 3 minus 3 is 0, 4 minus 3 is 1. So 2 comma negative 1 closed at that endpoint, 3 comma 0, 4 comma 1, and the graph continues, and I guess we get the idea what happens there. There's the graph of our piecewise function. For the last two exercises, we're given the graph and asked to write its equation. So h of x has 3 pieces, and the first piece is this piece over here on the left side. I would suggest starting with the left side. And if we can see there, the graph is pointing to the left of negative 2 with an open circle. That means that our x's will be less than negative 2. If you want to take the graph and simply just re-record it so all the points are on the x-axis, you can see the graph of x is less than negative 2 in one dimension. All right, from here we need to figure out what the equation of this line is. And to do so, I'm going to suggest that we take this piece of the function and extend it very accurately in both directions, and then look at this red line. What I can observe here is that my slope is 1 over 1, which is 1, and then my y-intercept is 2, so that's my b value. So written in y equals mx plus b form, the y value is 1x, which is x, plus 2. Notice that you don't need a y equals when you write this because you already have h of x equals on one side of the equation from the brace. Now let's take the second piece of the function. We can see from the second piece of the function, if you look at it just on the x-axis, that it is the values that fall in between negative 2 and 1, where negative 2 is included and 1 is not. And then we can take a look at the original, or rather at that piece of the function, and I don't think we need to extend it here, but our slope is negative 1, and the y-intercept, which is where the graph goes through the y-axis, is equal to 0. So in y equals mx plus b form, the equation of this line is y is equal to negative 1x plus 0, which is negative x in simplified form. Now let's take a look at the last piece of the function. If we look at it resolved to the x-axis, we can see that the x's are between 1 and 4, inclusive of both endpoints. And if we were to extend the graph, you can see that the graph is a horizontal line, and all the y-coordinates on the horizontal line are 5. So the equation of this line is a horizontal line, y is equal to 5. Remember, a horizontal line always has an equation in the form y equals a number. And there's our piecewise function. For the last one, we again have 3 pieces. And if I take a look at the leftmost piece has an open circle on 0 and goes to the left. So that's for x less than 0. And that piece looks like our parent function for y equals x squared. So this is just y is equal to x squared, or p of x is equal to x squared for x less than 0. The next piece of our function is resolved to the x-axis. The piece that goes from 0 to 2. So we'll write for 0 is less than or equal to x is less than 2. And for this piece of the function, the equation of the line extended would be the equation of a horizontal line, which is always in y equals a number form. Y is equal to negative 3. And now for the last piece of the function, If we just look at on the x-axis, we have an open circle on x equals 2, and we have a closed circle on x equals 2, and the graph is pointing to the right, so that is for x values that are greater than or equal to 2. And for this portion, it may be helpful to extend the graph so that we can see where the y-intercept is. And our y-intercept is -1. And the slope of this graph, m, is equal to 1. So the y is equal to 1x minus 1, or just x minus 1 in simplified form. And that is it.